So we said there was a possibility that we could achieve the ability to answer rank queries, but using an amount of space that was growing sublinearly in the length of the bit vector, small o of n, where n is the number of bits in the bit vector. So in this lecture, we're going to learn how to do this for the rank query. And this is using an approach called Jacobson's rank. It's from the idea is originally from a PhD thesis from this guy, Guy Joseph Jacobson, citation at the bottom. And it's going to be somewhat complicated, and as we get to select is going to be even more complicated. But it basically comes down to trying to divide up the problem, or trying to add layers of indirection to the problem, so that at the bottom, at the base case, we end up in one of two situations. Either we're considering a bit vector, or a piece of a bit vector, that is sparse, right? It has not very many ones in it, and lots of zeros, to the point where it's so sparse that we can afford to simply write down the answer to the query for each of the, up to each of the positions in that bit vector, because there are so few ones. We can simply write down the answers, or more likely, partial answers that might be combined with other partial answers that we've stored elsewhere to this query. So that's one case, the sparse case. The other case is we end up with a bit vector that's small enough, it's got few enough bits in it, that we can actually simply use the bit vector and combine it with some other things to make it a key into a lookup table, and the lookup table simply has all the answers pre-calculated. These are basically the two base cases we're moving toward: the sufficiently sparse base case and the sufficiently short base case. Okay? And in all this discussion, we're going to be imagining that the query that we're trying to answer is the rank sub 1 query, right? So the rank sub 1. But all the same ideas can be applied. We simply reverse the roles of the ones and the zeros and apply the same approaches to be able to answer rank sub 0 queries. Okay, so let's take a look a little bit more closely. So let's say this is our bit vector. I'm calling it t. And let's say it's got n bits in it. Okay? And I'm just using some color to make it easy to see the beginning and the end and the shades in between. And the first thing we're going to do is just split it up into equal-sized chunks. And we're going to pick a special size for each of those equal-sized chunks. We're going to say that they're each log base 2 squared of n bits. Right? So log base 2 of n quantity squared. That's how many bits that we're going to include in each of these partitions. Chunks. Let's call them chunks. Okay, so let's say here they are. So let's say each of these is a chunk, and therefore each one of them has that prescribed length. Log base 2 of n quantity squared, which we can write this way. And so how many of these are there? Well, it's just n divided by that, right? It's n divided by how many bits there are per chunk. Let's assume let's say that there aren't any issues with, let's just assume that n is a multiple of the log base 2 squared of n, right? So that this divides evenly. Okay? And then also let's just remind ourselves about this notation. When we put the 2 in the subscript, obviously, is the base of the log, but the 2 in the superscript is the same thing as saying log base 2 of n quantity squared, right? So it's just a sort of shorthand way of saying that. And by way of another note about notation, I'm not going to keep writing log base 2. I'll just write log, and throughout you can assume that I mean the log base 2. Okay, so this is the first step of the divide and conquer. We've taken our length n bit vector and divided it up into chunks of length log base 2 of n squared. Okay? So we can store, let's say that we store for each of these chunks a partial answer to the rank query. Now, what is the rank query again? Well, the rank query is I give it an offset. We give it an offset. It tells us how many ones there are up to but not including that offset within the bit vector. Okay, so the input is an offset and the output is a rank, the number of ones up to that offset. Okay, so what if for each of these chunks that we've just come up with, we store a pre-calculated cumulative rank up to each chunk? In other words, for this very first chunk, it won't be very interesting because there's nothing before that chunk, so the pre-calculated cumulative rank up to that chunk will be 0. But then for this chunk right here, the pre-calculated cumulative rank will equal the number of ones there are in this chunk, right? And for this chunk, the pre-calculated cumulative rank will be the number of ones in both these chunks, and so on. So let's say we store this, okay? So these little green rectangles are showing you for each of the chunks we're now storing a number, the pre-calculated cumulative rank up to that chunk. And let's think about how big the cumulative ranks are. Okay, well, how many of them are there? Well, I've got n over log squared of n chunks, and I'm storing one of them per chunk. And how much space do I need to store one of these cumulative ranks? Well, the cumulative rank, if we're not making any assumptions about how many ones there might be in this bit vector, the bit vector might, for example, be very, very dense with ones. It might have many, many, many ones. Well, then in general, the number of ones, the number of things we're counting to go into this cumulative rank, can approach n. Like it can get up to almost as high as n. So it would be reasonable to say that the big O space required would be this first term, which is the number of chunks. So it's the number of pre-calculated cumulative ranks. And then we're going to multiply that by log n, which is how much space we need to store one rank. So this is to store one cumulative rank. Okay, and this is the number of chunks. The important thing is, once we put it in the big O like this, right, this, maybe I should draw another set of parentheses, this log squared n over here is in the denominator. So this square will cancel with this log n. Okay, and we will end up with log n times, we will end up with big O of n over log n. So this is something that grows slower than n, right? It grows sublinearly with n. In other words, it is little o of n. So far, what have we done? We've divided our bit vector into chunks. We've stored for each chunk the cumulative rank up to that chunk. And that storage that we need for those cumulative ranks in total so far is still little o of n. It's growing more slowly than n. Okay. And so we've partly solved the problem because we've got these cumulative ranks, but we haven't entirely solved the problem. And so the problem now looks like if we want to find a rank, we decompose it into two parts. First of all, we figure out what chunk is it in, and we just need to do a division to figure out what chunk it's in. We just divide by log squared of n. Then we look up the cumulative rank for that chunk because that almost tells us the answer, right? It tells us the answer up to the beginning of the chunk, but that's not the whole answer because we now need to know within the chunk. What's my, you might call it, relative rank? So with respect to the beginning of the chunk, how many ones are there from there to where I am, to where the query is pointing in the middle of the chunk? And once I figure that out, all I have to do is add it to the cumulative rank that I've already looked up, and that will be the answer to the rank query. But we haven't done part C yet. We still need to figure out how do we find the relative rank within the chunk. Okay, so let's look at one chunk and think about what we can do to further subdivide the problem. All right, so here's one chunk. Let's say that a chunk can itself be divided into smaller pieces, and let's call them subchunks. So now we must refer to chunks. These are the log squared of n original partitioning of the bit string. And now we're going to take the chunks and divide them into subchunks. And how many bits are there going to be in each subchunk? There are going to be 1/2 log n bits in each subchunk, okay? All right. And the whole thing has to, right, so if this is the number of bits per subchunk, then this is the number of subchunks, and you multiply the two, and you get the log squared n, which is the size of a chunk. Okay, so let's visualize that. If this whole thing, this whole box, is my chunk, then each of these blue strips that I'm drawing inside, now as sort of like rows, those are the subchunks. And so there are 2 log n of them, so there's sort of like 2 log n rows, the way I've drawn the picture. And the width of one of the subchunks is 1/2 log n. All right, so far so good. Now let's say that, kind of like before when we said we would store the cumulative ranks up to the beginnings of the chunks, let's now store the relative cumulative rank up to the beginnings of the subchunks. What is the word relative doing here? Well, because I'm not going to count the rank going all the way back to the beginning of the sequence t. I don't need to, because I already have the cumulative rank up to my chunk. So I only need to store the additional number of ones that I would see from the beginning of the chunk to the beginning of the subchunk. That's why I'm calling it relative. It's relative to the chunk as opposed to being relative to the overall bit string, the overall vector. Okay, so these are relative cumulative ranks from the beginning of the chunk. And the key insight here is that in order to store a relative rank from the beginning of the chunk, I'm not going to need, like I said before, I'm not going to need log n bits to store one of those. That's how many bits, I needed big O log n bits to store one of the cumulative ranks up to the beginning of the chunk. But when we're in subchunk land, it's going to turn out that we only need big O of log of n bits. Okay, well, why is this? Let's take a look at why this is. Well, because each chunk only has log squared of n bits in it. A relative cumulative rank only really needs to add up to what basically the most ones you can possibly have in a chunk. But the most ones you can possibly have in a chunk is just the most bits you can possibly have in a chunk. And the most bits you can possibly have in a chunk, the way we defined it, is log squared of n. Well, so how many bits do you need to represent up to log squared of n things? Well, you need to take the log of it, right? So you end up with log squared of n. Now the outer log, the log that the sort of left-hand log here, means that the 2 can come down as a multiplicative constant, and then once we put big O around it, the multiplicative constants disappear, and so what we get is big O of log n bits. Right? So it's because it's a relative cumulative rank, we don't need log squared of n, we don't need log of n bits in order to store it. We only need big O of log n bits to store it. So if we consider that the number of bits we need to store one of these relative cumulative ranks is big O of log n, and we consider, well, how many subchunks are there total? We can, or what's the length of a subchunk? It's 1/2 log n. We can write down that if we have n log n subchunks overall, and over log n subchunks overall, big O of n over log n, because each one of them is 1/2 log n long, then we multiply those two together, we get n times log n over log n to get the big O number of bits we need for all of the relative cumulative ranks. And that is also little o of n. Right? N times log n over log n is little o of n. It's slightly sublinear in n. So we've solved even more of the problem now. And we need to store these cumulative ranks up to each chunk and these relative cumulative ranks up to each subchunk. But now we've solved the problem all the way up to the beginning of the subchunk. So far so good. But there's still more of the problem to be solved because after all, so if this is now an elaborated version of what we said before. So okay, well the first thing we need to do is figure out what chunk are we in, and we can do some division to figure that out. Then for that chunk, we should look up its cumulative rank. Great. Then to find the rank within the chunk, that's what we're working on now, we want to now figure out what subchunk are we in, and that's another division, right? We're going to divide by the length of a subchunk, which is 1/2 log n. And then we want to look up the relative cumulative rank for that subchunk. So now we have two pieces of the puzzle, but there's a final piece of the puzzle, which is we need to know what's our offset within the subchunk. Okay, so now we need to find rank within subchunk. That's to do. Okay, so now the final piece of the puzzle, we have the cumulative rank up to the chunk, the relative cumulative rank up to the subchunk. Now we need to do the work within the subchunk to figure out what's the relative rank within the subchunk. And there are basically two ways of thinking about this. One of them is to say, well, you know what, subchunks being only 1/2 log n bits long are pretty darn small. In fact, they're small enough that probably the entire subchunk, right, which being just 1/2 log n bits long, could probably fit in a single machine word. And now suddenly we can imagine that the computer processor might have a handful of instructions that we can execute. You know, an example of an instruction that could really help us out in this circumstance is what's called a population count, right? It's literally an instruction that counts the number of ones in a machine word. That's obviously very relevant here. So we could say that, well, we can use a constant number of instructions and solve the rest of the problem within the subchunk. It's really just a trick of making sure we get exactly the right bitwise operations so that we're selecting the bits we're interested in, and then we're able to count them in a constant amount of time, a constant work. So that's one way of thinking about it. But a second way of thinking about it is to say that we're in the second of the two types of base case that we talked about at the beginning, where now the bit vector is so short, 1/2 log n, that we could imagine making a lookup table that contains all the answers. And the bit vector itself, together with the offset we're interested in, can form a key for a direct address lookup into a lookup table. Okay, so let's think about this lookup table option. Let's say we go ahead and, naively store the answers to all possible rank queries for all possible bit vectors of length x. Right, just let this be a variable for now. Later we're going to plug in 1/2 log n, but let's just let it be a variable for now. How many bits are required? What's the sort of big O number of bits I need to store all these answers? So there are 2 to the x possible bit vector sequences of length x, right? So we need all of those are possibilities. And then we also need to store a different answer for all possible offsets within that bit vector, right? The rank query could be asking about some prefix of that bit vector. So we need to be able to store an answer for every possible offset into that x long bit vector. So that's x more answers. And then, of course, we need to be able to write down the number of, we need to have the answer in our table. So we need the number of bits to store our answer. That's going to be log of the number of bits in our bit vector. So that's log x. So if we really want to store a lookup table that has the answers to every possible rank query, well, there are 2 to the x times x such answers, and each of them require log x bits to write down. And what do we have to plug in for x? Well, we have to plug in 1/2 log n, because that's the width of one of our subchunks. So what happens when we do that? So we're going to plug in 1/2 log n here in the exponent. And we're going to plug in 1/2 log n down here. And then we're going to plug in log of 1/2 log n. And then there's going to be a great big O around it. And one interesting thing that's going to happen is this is 2 to the 1/2 log n right here. Well, that's the same as saying, this is the same as saying 2 to the log n to the 1/2, which is square root of n. So we've now turned that first multiplicative term into square root of n. And then multiply the rest out. We have a square root of n term times a log n term times a log log n term. So we have a square root of n times a log n times a log log n term. And this is also little o of n. This is sublinear. Okay. So we can write down all the answers to all the subchunk level rank queries in a number of bits that is still little o of n. Now let's put it all together. So we've got these three different partial answers: the cumulative rank up to the chunk, the relative cumulative rank up to the subchunk, and then the lookup table that allows us to find the rank within the subchunk. How do we put them all together? Well, we go through an algorithm where first we take the parameter to the rank query, I, the offset up to which we'd like to calculate the rank. We do a division to figure out what chunk it's in. For that chunk, we look up the chunk's cumulative rank. Great. Now within the chunk, we do a division to figure out what subchunk we're in. We look up that subchunk's relative cumulative rank. Then the last part is we need to add on, we need to calculate one more relative rank, which is the relative rank within the subchunk. Then the final answer is simply going to be summing together the three things: the cumulative rank for the chunk, relative cumulative rank for the subchunk, and then the rank within the subchunk using the lookup table. This is the number of steps we have to go through here is clearly constant work, right? Nothing here depends on the length of the bit vector. Nothing here depends on anything other than these steps, these 7 steps. Each one of them is going to involve constant work, so overall we're looking at a constant time rank query. And of course, we also said that each of the 3 supplementary data structures we need to build, for the cumulative ranks, relative cumulative ranks, and for that big lookup table for subchunks, each of those is little o of n bits of space, so overall all of the auxiliary data structures are little o of n bits of space. Okay, so we have one of the 2 sets of performance characteristics that we were looking for. We have a way of answering rank queries that uses constant time, little o of n bits of space, and this is this Jacobson's rank approach that we were talking about. This does not yet allow us to answer select queries. We need another approach, something that's called Clark's select, in order to answer those queries. But many of the ideas that we developed here for Jacobson's rank are going to apply also for Clark's select. It's just going to be a little bit more of a more complicated dance with Clark's select. But we're already partway there.